Good morning, good afternoon, good evening, and welcome to the Friday Talk Show with your host Rajiv Kulkarni on Global Electronics. Today's date is July 17th, 2026, early morning 9 a.m. here in Dallas, Central Standard Time of US, and also 7:30 p.m. in the Indian Standard Time. Thank you for supporting Global Electronics by watching our show, by sharing our link, and subscribing to the channel. We request you to continue subscribing the channel so that we can bring more and more interesting topics with different guests. And one of our permanent guests, as you can see, Mr. Ambaprasad, has been contributing a lot to this community, electronics community. And today's topic is sequel of the series that we have been conducting for the last 6 episodes. Is a physics-based HSIO interface design, and today's episode is episode number 7. Today's title is Constant Variables in Off-Package Connections. The synopsis goes like this: in off-package, that is high-speed I/O connections, there are several constant variables, key parameters that remain fixed and must be tightly controlled to ensure signal integrity and compliance across designs. These constants form the backbone of reliable breakout and routing strategies. To discuss this and to present this, we invite Mr. Ambaprasad, who carries a wealth of experience in the last 4 decades plus in the PCB design, DFM, DFX, and also electronics manufacturing activities. He is based in Silicon Valley of India in Bangalore, the southern part of India. And welcome to the show, Mr. Ambaprasad. Good evening to you.
I'm setting. Yeah, it's okay. Can you hear me?
Yes, we can hear you. Good evening. How are you this evening?
Doing good.
Very good. So let's. Okay, excellent. So I'm going to share the screen right now so that we can present your presentation. And just hold on 1 second. Okay, here we go. We left it. It's on the full size. This is where we left last time, I guess.
Yeah. So this picture was appreciated by certain people. They personally called me and told this carries 3 to 4 pages worth of text. Is there in one picture? That's what they appreciated. So that's why I thought.
Like the phrase goes, the picture speaks louder than the words, right?
Yeah. Okay. So next page, please. Constant variables in off-package. In off-package. Off-package means last episode we covered from the die to the package, how we take the signals. Now we are trying to explain how the signals travel from the package to the PCB, or rather than within the package. From the die, it comes to some bumps, and from the bumps, it has to come to the redistribution layer. So how this travels, that's why I told constant variables. Technology keeps changing, but the physics remains the constant. And in one generation of chip, what was state of the art, it may be okay, but as the speeds increase, what worked in the previous generation may not work in the next generation. So that's what I was studying, constant variables. You keep running very fast to be in the same place.
Correct.
That's the issue. Go to next page, please. Agenda. I wanted to keep it as brief as possible. Off-chip connections, that's what we covered. Then now we are going to off-package connections, maybe within the package, from the chip to the package and package to the PCB. C4 and C5 evolution. C4 and C5, this is a very scientific language, but C4 and C5 means BGA balls, nothing more than that. But when we say BGA balls or something, it looks too pedestrian of a language. So all the technocrats and the packaging engineers, they call it as a C4 and C5. So what is C4, what is C5? I'll explain a little later. EMIR, electromigration and IR drop threat. Then I'm going to expand it further. EMIR at the shoreline. So what is shoreline also I will explain. Then in the last episode or previous to that, we were talking about in a system packaging, the whole system, we were telling scale up, scale out, and scale across. It is true for servers, data centers, and telecom. But still, sometimes we may have to pedal backwards and a pack. What would have been a PCB, we want to convert into a package. And what would have been a package, you want to convert into a chip. You scale down actually. You don't scale up, you scale down. You highly densification, that's called as a scale in. The terminology is scale in, but people don't use this actually because this happens within OSAT community and packaging community. But I will throw some light on. Next page, please. Just 1 minute. So here I shown 3 levels. Level 1 is off-chip, high-speed IOs. From the chip to the package, a lot of variables are there. You can go for a HBM or a heterogeneous integration or a GPU, XPU, whatever you call. Then level 2. Level 2 is from off-package. This is from the package. If it is a sort of a single package, it will go to the PCB directly. Otherwise, within a package, there can be a multi-tiered structure. We can see some 3-tiered structures are there here. That's how it goes, and finally it lands in the PCB. Level 3 is off-board, which we will cover a little later. It's not an issue. So today we are concentrating somewhere between level 1 and level 2. Still we are there only. Next page, please. So this is a cross-section of a package, advanced C4 flip chip BGA package. So C4 is controlled collapsible chip connection. C4, controlled collapsible chip connection. So when the BGA is soldered, the BGA ball will have a certain height. Already the top 20% or 10% of the BGA ball is chopped off to when you make a connection to the package. So when you make a connection to the PCB at the bottom, say 10%, that also will get integrated into your solder. So now the chip starts collapsing. If the height of the chip from the PCB floor to the chip, there will be a certain height. After the assembly process, this height will reduce. So it is a collapsible. So there are collapsible and non-collapsible bumps in a BGA, but we are talking about collapsible. So controlled collapsible, you have to control the collapse. It has to collapse uniformly. If it collapses certain degree more in some locations and certain degree less in some other locations, we see issues like warpage and missing connection, and there are a whole lot of defects over there. So we are assuming collapse is totally controlled. That's why it is called as a collapsible FCBGA package. We have shown a cross section over here. So what are we are seeing? We are seeing signal integrity challenges at 112 plus Gbps data transfer rate. And we are talking about ultra HDI wires. We have shown a cross section over there, how it looks like. Then PD and power distribution will happen. It may happen within the BGA or within the package or within the die, within the package and within PCB also. This is another diverse problem. And thermomechanical reliability, which we also will lead to electromigration and IR drop. So this is purely electromechanical, thermo-electromechanical sort of a defect. So, but all these are physics-based, rather multi-physics-based. Each one will affect the other. If there is too much of stress here, this will spoil signal integrity and power integrity. or there is too much of power overload, this will lead to IR drop. And this is a very cyclic. This keeps on happening. And the simulators are available to simulate this before sign off. So I told this is what it is, constant variable. This keeps on changing, but the problem remains the same. Next page, please.
So one question is this particular design or the specification is related to any certain application like data center or anything like that, or is just a very generic explanation purpose?
Sounds good. Sounds good. It is generic actually. When the BGAs were made in 1996, first time when they came, the more or less its cross section remains the same. But the connectivity to the what we call as a pin map, the pin maps keeps changing. So it is right. It was the right time for you to ask this question. In a BGA, if when we talk about a BGA for say ordinary cell phone or something, its pin map is different. And let's say we do a BGA for aerospace, its pin map is different. But when we do the BGA for a data center or a telecom chip, it's it's a different animal by itself. So the pin mapping changes. But when we talk of high-speed I/O interfaces, you see this BGA has got four sides. I can say
Correct.
east and west and north and south. This extreme two rows and two columns, two rows over here and two columns over here, and two rows over here and two columns over here, they are called as a shoreline. That is a very coveted real estate. All high-speed interface IOs will originate there. Okay, they originate in this chip, they land in the other chip in the same location at the periphery. So this periphery is the two rows and two columns on east, west, north, south of a BGA is called as a shoreline. Okay, let's go to next page, please. So I have captured this. Some of this we covered in the synopsis. In advanced packaging, including 2.5D, 3D, it goes up to 5.5D now. Starting from 2.5D or 3D, chiplet architectures and high-density substrate designs. The breakout strategies for a C4, that is a first level interconnect. And the second level interconnect is C5. Second level interconnect. Packages provide the fundamental pillars of signal integrity, power integrity, and manufacturability. If the packaging fails, however good the PCB layout is and however good the chip is, this acts like a bridge in between. Okay, so this is the one which this is the business end of your package of your chip. The package is the business end. That is where we can measure actually.
Yeah.
Managing the electrical and mechanical transitions from micro-scale die pads to system-level boards require a distinct architectural trade-offs. So let's go to next page.
Wow.
So it starts from 2D. What we saw in the 1990s was a 2D. Then it became 3D, 2.5D. Up to 5.5D architectures are available according to IEEE. Maybe we can explain them in some other occasion if people demand that. If someone wants, they should say that they want it in our chat box. Or otherwise, if we have time, we do it. Otherwise, I want to maintain a flow in what I'm.
Correct.
So
Yeah.
here I have shown C4 connections here. C5 is used within the package. In PCB level, what we see is C4, and secondary level in a BGA. Now, for example, here the bump pitch can be 0.4 millimeter. Okay, but on a PCB we want 1 millimeter pitch BGA. Okay, so we convert this 0.4 into 1 mm by redistribution layer. So that is C4 and C5. So this gives its own challenges. I will try to capture some of them. Then I shown here this ball when it is assembled, it collapses a bit over here at the top end and at the bottom end. So that's why it is called as a control collapsible chip connection. Go to next page, please.
Wow.
So this diagram, we started 2000s up to the present. We are scaling package size 40 millimeter by 40 millimeter. In 2000 and 96 it started, but let's take it as 2000. Then by 2010 it became 55 by 55 millimeter. They are packaging more number of bumps over there. And by when you go to 2.5D interposer current chip level, 80 millimeter by 80 millimeter is the BGA size. So when you say 80 millimeter by 80 millimeter, 80 millimeter on north and south and 80 millimeter on east and west flanks of the BGA is called as the shoreline. That is where all high-speed IOs will concentrate. Advanced packaging, if you go ultra high density, advanced chiplet packaging, which is happening right now, it may become a reality by 2027 or 2028. There are 1 lakh pins within the whole package, and we are looking at 100 millimeter by 100 millimeter BGA size. It is becoming more challenging. Then bump count, 2010 almost 2000 pins. Then it became 4,000 by 2010s. It became 20,000 by 2010 end, 90 micron pitch. And it is 55 micron pitch at the first level, not at the second level, at the first level. And 1 lakh pins. These 1 lakh pins have to be routed. Imagine the job of a PCB layout designer. 1 lakh connections. We're talking of 1 lakh connections. Okay, it takes an entire team to do this. Then
So
C for
one,
bump.
so 1 lakh is 100,000 for the people who doesn't follow the Indian numbering system. Yeah.
That
Okay.
comma I put there actually, 100,000.
Yeah,
The comma has
100,000.
been,
Yeah. Yeah. Yeah.
the scary picture
Okay.
is telling 100,000 plus.
Yeah.
It is not 100,000, 100,000 plus. It could
Plus.
be
Yeah.
120,000 also or 140,000 also. But at least 30% of them will be ground pins. So don't get scared by signals will be less. Ground and power will be more. At least 30% will be ground. Another 15-20% will be power. So 50% will be the signal connections. 55 micron pitch at a secondary level. C for bump pitch, it was 130 micron, 127 micron, 90 micron, and 55 micron. Actually, when you want to manufacture a PCB, mechanical drilling 80 micron is cut off. If it is less than 80 microns, mechanical drilling is not possible in a PCB. That's why the foundries will spend a lot of time. They go to OSATs and they convert all their 55 micron in packaging to 80 micron in the secondary level packages, or 100 micron or 80 micron. Okay, next.
Okay. Let's take a break here and we'll come back.
Yeah.
Good morning, good afternoon, and good evening, and welcome back to the Friday Talk Show with your host Rajiv Kulkarni. As we know that we have been conducting this sequel of series called the physics-based HSIO, that's high-speed IOs interface design, and today's episode is episode number 7. And we have Mr. Amba Prasad, who is a technocrat and who is a technology expert, having more than 4 decades of experience, and he has been contributing a lot in the global electronics community. And our main objective is to share our wealth of knowledge that we have accumulated over a period of so many years, and to the electronics manufacturing community, so that people, the engineers and other people can get benefit out of it. And this particular electronics manufacturing topics include not only the design, not only the process, but also includes the market intel, the supply chain, and so on and so forth. If you want to be part of this show, please do write to us and send us your details, and definitely we will listen to you, and we will also feature you in our upcoming shows. So let's get back to our today's show, continue our show, and here we go. I'll share the screen again, and then we'll take it further from there. Mr. Amba Prasad, here we
Yep.
go.
Okay, keep it easy here. I want to put some numbers in the context.
Yeah,
The audience should understand what we are talking about.
correct.
And the PCB technology, for example, when electronics started, IC technology started in the 50s, 1000 mil was 1 inch. So 1000 mil. Almost up to 1996, 98, it went in mils only. All PCB layout designers, they can understand mill in and out. You tell them some other number, they want to reach to a calculator. But what happened in 1996 onwards, when the C4 scaling happened, first BGA came in 1996 was a 60 mil BGA, 1.5 to 4 mm. It shrunk, 20% was reduced. It lost to 20%. It became 50 mil actually, 1.27. 60 to 50 is 20% cut. 1.27, that was still a mill based. Then next generation would have been from 50, if we take 20% off, would have been a 40 mil BGA. Then routing, scaling, manufacturing, integrating is a big problem. Then JEDEC came into picture, JEDEC, IPC and all these institutions came into picture. They told enough of mills. Now let's go to millimeter and microns. So after 1 mm BGA, 1 mm BGA is a workhorse. It is even now it is there. A lot of chips will come in that. Almost 80% of the chips are manufactured with 1 mm BGA. Easy to remember 1 mm. Otherwise, 39.37005 mils, all that is gone out of the window. After 98, it is all millimeter or microns. So when it went to HDI and ultra HDI, it is only microns. People will never talk in mils anymore because the ICs, the die, they talk in microns. It also makes sense to talk in microns in PCB level also. So that's the rationale, and now it is very easy to calculate. So we don't lose any number, or we don't drop integers when we divide or multiply or convert. That way, even you convert millimeter to micron, you don't lose integers, only the point moves. That's it. So that is one good thing which has happened to the industry, that brought a lot of stability in the industry. So to put in the context, 1000 mil is 1 inch, 100 mil was a normal IC pin pitch, and 1000 micron is 1 millimeter. So when we talk about microns, 1000 micron is 1 millimeter. So all these numbers, if one wants to digest, this is what it is. I'll give you in the context. When we used a VME connector, we were drilling a 1 millimeter hole to put a connector pin. And now I'm talking of a BGA with 1 millimeter pitch. In one connector pin location, there can be 16 balls, 16 bumps. So that is a densification which we achieved actually. So it is a mind-boggling number. Okay, go to next page, please. I have given key parametrics for C4 packages. C5 we cover in the next session. So C4 still it is a workhorse, a 1 millimeter pitch BGA. Ultra low parasitic profile, the short physical length of the C4 bumps minimizes loop inductance and capacitance, which is absolutely critical for maintaining high margins in 112 Gbps or a 224 Gbps PAM4 TIE generation 6, 7 transmission lines. Signal integrity, it's very good. High pin density enables massive parallel bus structures, example HBM interfaces in dense localized power delivery networks directly under the high performance processing cores. Direct thermal dissipation, you can still go for a thermally enhanced BGA. Direct thermal dissipation provides a low thermal resistance path to the channel heat, channels the heat from the die hotspots down to the packaging and to the PCB. These are the strengths. Then the next page. Weakness, SWOT analysis I have done. Strength, weakness, opportunities and threats. That's what I did. Weakness, extreme routing density at a PCB level requires a sophisticated semi-additive process, SAP and MSAP when you are doing a packaging. On the substrate to resolve sub 10 micron line space traces drastically increasing substrate layer counts in a fabrication cost. That is from the die to the package. Severe near end crosstalk. The dense clustering of escape traces, especially at the shoreline, creates massive proximity-induced crosstalk, both far-end crosstalk and power supply-induced near-end crosstalk. Resolving this requires aggressive shielding and ground stitching vias, which further congest the routing channels. So I was telling, if you have a 1 lakh pins, what it means is about 30% of them are ground only. Not only they are used as a power supply ground, they're also used to as a shield ground. Okay, that is where the number of ground pins are exponentially increasing. Impedance discontinuities without highly optimized cutout zones, voiding reference planes directly under the C4 pads, capacitive loading of the bump interfaces can cause severe high frequency return loss, insertion loss as well as return loss. This is the problem, and this is generally simulated well in the package level. Then only the package, by the time it comes to the market, all these things would have been ironed out. Okay, next page, please. Opportunities, how to resolve the problems, shift left of the left core design, integrating breakout optimization at the pre-schematic die floor planning stage allows designers to coordinate through silicon via or a bump placement with substrate escape paths, minimizing routing revisions. Actually, the package is designed for a next generation. They leave pins empty for the next expansion. That's how they manage it. Advanced dielectric film integration utilizing the next generation build-up films like ABF, Ajinomoto build-up film. That's a brand actually. Formulations. So to dramatically reduce dielectric absorption and to enhance controlled impedance. Hybrid bonding evolution, transitioning from traditional solder C4 bumps to direct copper to copper hybrid bonding. So that is where the C5 comes into picture. Eliminating bump standoff height entirely by pushing parasitic inductance to almost zero. So this is how they are doing in a package design. Next page, please. Threats. This is generally EM-induced threats. Some of them are thermal, some of them are electromigration due to densification. Local CTE mismatch and shear stress on the C4 balls. The localized thermal expansion mismatch between the silicon die, approximately 2.6 ppm per degree change in centigrade, degree change. And organic substrate approximately 15, no, organic substrate is 15 ppm. Your package is 2.6 ppm. There will be a mismatch, a CTE mismatch. There will be a crack. Concentrates extreme mechanical strain on the peripheral C4 bumps, risking crack propagation during the rapid power cycling. This can happen even while assembly also. Electromigration, EM, high current densities packed into microscale C4 joints accelerate void formation at the intermetallic compound interfaces, threatening long-term system reliability. Substrate supply chain yields, this is a never-ending problem. Supply chain issues are always there because right now all AI chips, they are pre-booking the all materials. If someone wants to use that, they have to wait for almost 3 months. That is the waiting period right now. Substrate fabrication with sub 100 background C4 pitches remains a primary yield bottleneck for advanced OSATs. Next page, please. I just compared two scenarios, first level interconnect and second level interconnect, C4 and C5. Typical pitch 30 to 150 micron, 0.4 to 1 millimeter at C5. So this is how this becomes it is very easy to assemble in a PCB. Primary domain wafer level package substrate for C4. For C5 system board PCB. These are the board interface. System to board PCB. Dominant SI challenges, near field crosstalk and micro bump capacitive loading. Via stub reflection, return loss, fiber weave skew. These are shown in the first picture, what I was showing. Maybe we can repeat it when we do a deep dive. A dominant mechanical challenge, local CTE mismatch, silicon and to substrate, and electromigration. Global CTE mismatch, substrate to PCB, reflow, warpage while assembly. Key standard focus, IPC 2226 is for HDI and Ultra HDI. IPC test method 109 for a bump failure. IPC 2221, 2222 for PCB routing. And 6012F is for PCB acceptability, class 3 or class 3A. This is where we have to look, not even at class 2, class 3 or class 3A. Next page, please. I think only one more slide after this. Electromigration and IR drop. This will explain what it is maybe going forward. This happens at the shoreline also. This happen at the core areas also. But shoreline it happens. This will lead to warpage as well as high-speed IOs which are concentrating on the shoreline. They get degradation. So these are the challenges. Go to next page, please. I think this is the last page. Let me check up.
Yeah.
No, there is one more.
No, it's this is the last.
One.
This is the last one.
There is one more after that, which is a curtain riser for the next thing.
This
go
one.
To the previous. Yeah, go to previous. Yeah, keep it. So, no, next page. Just click once. Yeah, just stand there. So this is at a package level or even it can be applicable to PCB level also. I have very clearly shown where the shoreline is at the two extreme corner, extreme edges of the BGA. XPU die is there. They are using an interposer. They have gone to secondary level redistribution. Then they are going to the package. Here you find high-speed traces routed like transmission lines. Then you have power supply planes. Then simulation is done. There is a via. Electromigration happens. Visualization are given. Why it happens? This I can explain a little later. Not an issue. Then go to next page. There is the last page. Click once again. Yeah. So to counter all these problems, the industries started with 2D packaging. It went to 2.5D packaging, went to 3D packaging, up to 5.5D packaging is available. They're used in certain levels. For HBM, they use something different. For GPU, they use something different. For XPU, they use something different. So I just explained what are the advantages over here. These are generally done by OSATs. And JEDEC has got its own formula. They give a pin map, they give pin spacing. So if we follow JEDEC outline or any industry standard outline, industry MSA outline, it is called as a registered package. Like in the previous episode, I showed Mavericks, they try to do something different. If they try to do on their own, it is called as a non-registered package. So that is the difference between a registered package and a non-registered package. So that was my last slide. As usual, we take up this as a next and we propagate. So next episode, I try to explain as and when it happens, that is. I explain the challenges, assembly challenges and fan-out challenges, as well as I explain what is called as scale up or scale out, scale in. When you do scale in, when we are talking of a shoreline, right now, let's say we have a 40 millimeter by a 40 millimeter BGA, our shoreline is 40 millimeter by 40 millimeter. But if you go for a 5.5D or something else heterogeneous packaging, it is not 40 millimeter by 40 millimeter. Okay. You can even enhance it. You can have one more tire, you can have a multi-tire packaging. You can go through a cable or you can go through a what is called as a flyover. This is one of the names they are given. So then you can increase the IO outlets. The shoreline can be enhanced. So imagine you have two beaches. So generally you have only one beach, one shoreline. Imagine you have two shorelines. Generally your ships can come and go very fast, right? Or it's only in theory, but in electronics it is possible. You can have two shorelines in a multi-tier structure. That is called as scale in packaging. Thank you for listening. I think too much of technical explanation and physics crept in today, but that's how the industry is working. That's why we called it as a physics-based HSIO router.
HSIO interface, yes, that is correct. And I thank you, Mr. Ambaprasad, for being one of the strongest supporter and also participating in a weekly global electronics talk show. So to the viewers, thank you all for watching today's show, and wherever and whichever part of the world you are watching it from, we really thank you for your support, and we request you to kindly share our channel's link with your other colleagues and friends in the electronics community so that they can also avail the benefit of this wealth of knowledge that our guests who share after serving the electronics community for so long and so forth. With that said, we'll come back again at the same time next week with yet another topic. We don't know yet. Go ahead, Mr. Ambaprasad.
Yeah, I was talking about BGA, ball grid array and all. Now it is a football season. So when you say ball, people don't see microns, they see a very big ball. So in fact, even in that, the ball, what they used in a football, there was electronics inside that.
Yeah.
To have that line, it was a smart ball actually.
Smart
so
ball.
Technology went into that. So that's it. You cannot
Thank
escape. Even if you want to play football, you cannot escape electronics. So that's where electronics changes you actually.
Absolutely so true. Absolutely
football,
true.
This weekend, enjoy whichever team you are supporting. Please enjoy. So I enjoyed football season very well. Good.
Thank you, Mr. Ambaprasad. And again, I was saying to all the viewers, thank you for watching and supporting the show, as always you do. And our main objective and aim is to support the electronics community in the electronics manufacturing sector. And as I always say that if you are interested in any particular topic, please do mention that in our YouTube comments section, that what topic you are interested in, and if you would like to present the topic, you are more than welcome to do that. With that said, this is your host Rajiv Kulkarni signing off at another edition of Global Electronics talk show on Friday. Thank you very much. Have a great weekend. Bye now.